Hello, my name is Kurt Johanns, and I'm here today from KLA Instruments to talk to you about the role of nanoindentation in the fabrication of semiconductor devices. Before we get started in this presentation, I do want to thank Toyo for inviting me to give this talk. Toyo is a very loyal distributor of our products and have been with us for many years, and it's my absolute pleasure to work with them. As I said, my name is Kurt Johanns. I'm an application scientist here at KLA Instruments. I've been with KLA for about 5 years now, and but overall I've been practicing nanoindentation for about 15 years. Some of my experience is in the fracture and failure of ceramics, along with testing of metals, and among other things. So moving into the presentation, today, again, as I mentioned, we're going to talk about nanoindentation in semiconductor devices. Overall, we're going to talk a little bit about the nanoindentation process very briefly, and some of the measurements that nanoindenters are capable of making in this industry. But I really want to spend the bulk of this presentation in talking about specific examples of how nanoindenters are being used currently and where we foresee more use of nanoindenters in semiconductor manufacturing. Primarily, people think of hardness and elastic modulus when you think of a nanoindenter. I want to take a step back and think about nanoindenters from a broader level. And really, nanoindenters provide three huge pieces of information for industries like this. Mainly flexibility, right? How bendy is something? The strength of the material. How strong is this? And failure. Nanoindenters can probe failure and they can create failures, and by doing that we can examine other material properties and other characteristics of during the manufacturing process. So we'll wrap all of this up with a summary at the very end. Now I've put this picture up here not for any specific reason, but I want to highlight all of the types of materials that are involved in the manufacturing of semiconductor devices. It's metals, ceramics, polymers from broad category. It's ultra thin films. It's different types of deposition techniques. It's different microstructures. The array of materials being used in these devices is massive. And nanoindenters are really a great way of probing these materials prior to manufacturing, during manufacturing, and then post-test characterization, post-creation characterization. So we're going to get into this a little bit more. So why KLA nanoindenters for the semiconductor industry? And again, this goes back to people mainly think of hardness and elastic modulus, but in reality, you can do so much more with nanoindenters, and that's because they're very highly controlled devices. So KLA nanoindenters, they simulate contact, right? There's a lot of contact going on in these types of devices. We can target and test small features. We can detect the onset of cracking. We can force cracking and detect when that happens. During a contact event. We can measure different types of materials all the way from substrates down to ultra thin films on the order of 10, 20 nanometers. We can measure local strength and elasticity, which is very important. This again goes back to hardness and elastic modulus. Fracture toughness. And then when you move towards the polymers and time-dependent materials, we can look at local dynamic mechanical properties of polymers. And then you go into metals and time-dependent plastic deformation. We can look at stress-driven creep, material transport. So the range of tests is well beyond the standard hardness and elastic modulus. It's really a nanoindenter is really a tool to probe these devices and learn something, whether you're in quality control, R&D, or any point along the manufacturing path. Okay, so that's great, but why not standard testing devices, things that have been around for 100 years to measure these materials? And the answer is twofold. The first reason is characterizing as produced, as manufactured materials in these devices. You can't go to traditional testing. The sizes are too small, the shapes are incorrect. You can't apply traditional testing techniques. So that's where the nanoindenter comes in. You can control the size with the indenter itself, and you can also target very small features. So the size and the state of the components is not attuned to traditional testing, but a nano indenter can test. The other thing is as materials get smaller, as the push for faster electronics is being made, microstructure changes, right? And so as example in this, when you're depositing metallic films, grains shrink with film thickness size, right? So testing a bulk material of the same metal is not the same as what you might expect in the as manufactured piece. Similar with polymers. Polymers now, chains have to start accommodating local deformation. They have to fit inside a forced volume. And this changes mechanical behavior. And then thus you need to test it. And a nano indenter is really one of the only tools that is able to probe these materials and such a wide range of materials and sizes. Finally, as we'll look in a little bit later here, as we look at the failure section, interfaces start playing a very strong role as volumes shrink, right? When you have millimeter type coatings and bulk substrates, the interface plays a small role. But as you shrink the size of these films and deposition techniques, and you're looking at grains and adhesion of films on different substrates, that interface becomes more and more critical as things shrink. And we'll explore that a little bit in the failure section. Okay, so briefly, we're going to talk about what does a nano indenter do. Basically, it's controlled instrumented indentation, meaning we apply forces in a very controlled manner, and we measure displacements very, very accurately. And the standard test is very simple. This is a load time curve here. We apply a loading, and then we perform an unloading of that same load. And we can do this with many different tip geometries, and we can control the size of the loads down to micronewtons all the way up to newtons of force. So a very dynamic range of loading capabilities. And the outcome of that is a couple of things. One, you get these residual impressions, typically residual impressions after the loading event, showing where the indentation site hit. And you get data out of this. And the most kind of standard way of looking at data is a load versus indentation depth curve. And traditionally people think of the loading as being an elastic plastic event and the unloading as an elastic event. So the unloading being an elastic recovery, we can then use some contact mechanics models and come up with an estimate of the elastic modulus of that material, right? At very, very small scales. The loading event is inducing plastic deformation typically in these types of materials. And so there we can quantify the hardness or the strength of these materials with this. So we get hardness and elastic modulus from these load and unload curves. And amongst all the other stuff we can do here as we'll explore later. Okay, so let's focus now a little bit more towards the semiconductor application. And where are nano indenters and what kind of applications are we looking at? And I'm not going to go through this entire list. You can certainly we'll read through this list on your own. But we're involved in front of the line, back end of the line, and packaging processes in the semiconductor industry. And so we're looking at failure analysis labs. We're looking at gels for environmental protection. We're looking at solder bumps and micro pillars for maybe LED applications. And thin films has been a staple of nano indenters since the very beginning. It's really why nano indenters were designed. More specifically, you can look at film adhesion energy, film strength as an example. We can change temperature during these tests, encapsulation, as we mentioned, lots and lots of different applications in various parts of the manufacturing process of these semiconductors. And what I want to do is go into some kind of very specific examples next. A little bit more information about where nano indenters play a role. This is a kind of just a schematic of the semiconductor manufacturing process. And semiconductor manufacturing starts at the university level or the research level, right? And going back to materials are different at small scales, that's what research is mostly about for folks doing nano indentation, trying to understand small scale mechanical behavior. As they learn about that propagates towards R&D labs associated with semiconductor folks. And they're taking these new materials and seeing how can I fit this into my process and can I make it work at a large scale manufacturing event. So then there's materials and components going into these things. There's polymer coatings, there's film deposition. You get into the fab itself, and now you have crystal growth, cleaning, epitaxy, wafer fab. Lots of things are happening here. Here's we're looking at films now again. We're looking at pillar and bump bonding. And often there's failures, right? There is some sort of yield out of these plants, and they want to improve yield. To do that, they go to failure analysis labs. And again, nano-indenters are a critical role here because we can probe the strength, flexibility, and failure of these materials. That information feeds back into the R&D lab. They make changes and propagate that down to the fab line, right? Once it's all done, once it's all created, or even have nano-indenters looking at the final product, looking at underfill polymers, environmental protection, making sure the strength and flexibility of the packaging is appropriate for the device, right? So lots of applications and lots of places where a nano-indenter can fit into this process that traditionally maybe you didn't think about. Traditionally, nano-indenters are down here at the university level and R&D lab, but there are certainly a number of applications and locations where nano-indenters fit along the line. Okay, so again, as I mentioned, this presentation is mainly focused on specific examples. And the reason for that is I don't want to get into the science behind these things. I want to be able to spark your imagination of where nano-indenters can play a role in maybe your process or other processes in the semiconductor line. So specific examples, as I mentioned, nano-indenters probe the flexibility, strength, and failure of materials. Under the flexibility section, we're going to look at gallium nitride for micro LED applications. We'll look at some silicon carbide results, and then as we move towards very, very thin films, we've got to characterize them, and nano-indenters are perfectly suited for that. Under the strength category, we're going to look at micropillar yield strength, some rate-sensitive hardness, and stress migration or creep testing, right? So this is all plasticity-dominated strength type measurements. And last, and maybe my favorite, is failure mechanisms. How can a nano-indenter help us understand failure? So we'll look at crack resistance and deflection, some piezo-on insulator for 5G applications, and delamination of low-K dielectric thin films. Okay? And really what this comes down to, this diagram, which is the kind of the fundamental material science diagram, is for semiconductors, you have to have device reliability. They're also trying to shrink the size of these devices, and you need performance. So these three things are kind of driving semiconductor manufacturing, and it's pretty unique that mechanical properties start to play even a more and more greater role as we're trying to improve these three circles on the diagram, which is not intuitive. Intuitively, you might think electrical properties are important and things like this, but mechanical properties are playing a stronger and stronger role. And that's because this volume is shrinking and material performance is much more important. Okay, so again, getting into some examples. The first one we'll look at here is gallium nitride layers for LED applications. And this example here is nano-indentation using a cube-cornered indenter to probe the flexibility, strength, and failure. In this case, in this one example, all three measurements of these gallium nitride layers on sapphire. And as a side note here, KLA is very good at examining defects in semiconductor devices, especially on wafers. And so one of our systems was seeing these defects in gallium nitride, and they sent the wafer to us in the nano-indenter community, in nano-indenter section, and said, hey, can you tell us a little bit more about this? So we started probing, and we did some indents at higher loads, and we see cracking going on. This cracking was matching up very closely with the types of cracking that they were seeing in this defect inspection. And so we said, all right, well, we see cracking, and we can see spatial variation in this cracking. But we can also go and look and measure the flexibility of the film relative to the substrate, right? So we know the substrate is very stiff. It's sapphire. Well, how stiff is the film itself? And it's also very stiff, not as stiff as sapphire, but this is important because this cracking is occurring at the interface, and a lot of this cracking is driven by elastic mismatches and stress-driven mismatches. So you have a more compliant film, still very stiff, but more compliant film on a very stiff substrate. And that's important to know. And how is this elastic modulus mismatch playing a role in the fracture? The other thing we can look at is during the indentation test, we see evidence of crack initiation or local failure strength. We can see these what we call pop-ins and the initiation of cone cracking in the load depth curve. And so ultimately for this customer, where we had multiple tools like KLA helping design better materials, the solution is local characterization of elastic modulus, hardness, and stress-induced fracture. We've identified failure in gallium nitride layers before it got to the market, and helps them design and tweak their deposition process. And further, they can take this data, put it into their finite element solutions, simulations, and try to improve yield. So again, gallium nitride layers and a single indent can provide a wealth of information. Okay, another example for power electronics, high power electronics, is silicon carbide. Silicon carbide substrates are very critical right now, and it's all about stiffness, stress and stiffness, and getting rid of defects, right? So when you think of those two things, the important there is flexibility when you think of stiffness. And silicon carbide is a very anisotropic material. So depending on the orientation, you get very much different elastic modulus response or elastic modulus measurement. So for example, this is silicon carbide 6H, and we have two different directions, one along the basal plane and another along a different plane. And as you might expect, we measure an elastic modulus that's different between these two. And this is critical because a lot of stuff that is driving this failure is elastic mismatches. And so as the semiconductor manufacturers are tuning in the right modulus by changing crystal orientation, nano indenters can help measure that. Further, the strength of these materials is also orientation dependent. And that's gonna help mitigate defect creation, and then how do you get rid of these defects, right? So again, the nano indenter can help us characterize very stiff, very hard materials very, very rapidly. Okay, the third one that I want to talk about for nano indenters and flexibility is measuring thin films. And again, this goes back to, you have a very small, thin layer of material. Traditional techniques don't always work for this case. So nano indenters come into play, and what we can do is start with the continuous stiffness measurement, CSM technique with KLA nano indenters. We can start making these elastic modulus measurements right from the very top of the thin film, and then continuously as we penetrate into the film. And what we see, typically, as an example, this is a low-K dielectric material. We're measuring, so it's a porous glass. We're measuring an elastic modulus somewhere around 10 gigapascals. And as we continue to push into the film, we measure a continuously rising elastic modulus. And the question is, and what the manufacturers need is, what is the answer? What am I supposed to pick? What number do I pick off of this chart? And you might imagine at small scales, the film dominates, and at deeper scales, the substrate dominates. The size of the indent is so large that all you're kind of measuring now is just the substrate. So why is that? As a very duckies and horses example, to put it, what's happening is we're generating elastic and plastic stresses in the film during the indentation process. But because the film is small relative to the substrate, and as the indent size gets bigger and bigger, we start to propagate these stresses into the substrate. And thus you might imagine then these elastic stresses are going to affect the elastic modulus measurement. And then this is not unlike a very crude example here is we'll call a s'more. And a s'more is these very stiff, in this example, a very stiff film on a very compliant substrate. And you can imagine as you apply stresses or you push down on this graham cracker on top, the substrate's going to deform. And we need to remove that. We need to, if we're going to make an accurate measurement of the elastic modulus of the film itself, we need to be able to get rid of the substrate response. And that's exactly what KLA nano indenters do. And we call this CSM, continuous stiffness measurement, plus AccuFilm, a thin film analysis. So we take this standard indentation data as a function of depth. We plug it into a very simple model developed by Jennifer Hay and Brian Crawford a couple of years ago. And the outcome of this is this colored data down here. So this is film elastic modulus as a function of depth. And now we're measuring a relatively constant elastic modulus for this film, which is what we expect, as a function of indentation depth, right? The original curve here has the substrate affected modulus, and then the corrected modulus is down here. And what I want to point out is even at very shallow depths relative to the film thickness, the correction can be large. This is, as an example here at 60 nanometers, this is 6 gigapascals versus 8 gigapascals. That's a 25% change. And that's very critical to some of these models for low-K dielectrics. The difference between 6 and 8 GPa is tremendous, right? So AccuFilm gives us substrate-independent measurements of thin films. These are results that are insensitive to depth. So we're now measuring the true dependence, the true film elastic modulus. And not only that, we also get a 50% reduction in standard deviation. So this model really cleans a lot of things up. And that, in the end, provides increased sensitivity to detect smaller changes in processing, which are very critical to assessing the flexibility of these films. Okay, last example for the flexibility is ultra thin films. So as we move down towards these 10 nanometer, 20 nanometer type films, we need to be able to measure very, very small contact depths and measure properties there. So as an example here, this is these are load displacement curves, both these graphs. On the left here, this is in 111 silicon, and on the right is on a sapphire substrate. And the whole goal of this testing was to make small as indent as possible and still measure the correct elastic modulus on these well-known materials. And so if we do that in silicon, we can apply, the maximum here is 50 micronewtons, and we get to about 10 nanometers in that case. On the sapphire, we apply 30 micronewtons in this example, and we get to 4 nanometers of indentation depth. So very, very small indent depths. And as you might imagine in the sapphire, a very, very low displacement curve that's very elastic, right? We haven't initiated plastic deformation yet, as you might expect in this very hard material. When you go and you look at the modulus results from 3 different loads in silicon, where we really, really know the answer to elastic modulus, we come up with the correct values, the expected values. A little bit of scatter in the 10 micronewtons, but that's also down here at 3 nanometers of depth, right? So really pushing the boundaries of nano indentation here, and because we need to measure these ultra thin films. Okay, so that was flexibility, mixed in with a few other things. That was flexibility. And now I want to talk a little bit about strength and hardness of small features. So again, measuring the strength of a bulk material in a traditional tensile test environment, and then applying those properties to the deposited material at very small scales is not always good. In fact, it's been shown quite a number of times that it's incorrect to do so. So nano indenters become the way of measuring local strength of these materials, and we do this through hardness. So we can look at crushing micropillars, metallic micropillars, and examining strength that way. And then in some cases we can even apply kind of some unique testing where we're measuring the strength and fracture of ceramic pillars, very, very local stuff. And in this example, this is a function of temperature in this case. We do this with nano positioning devices and optical microscopy for the most part. We can do this inside an SEM, but most of the time, especially for our semiconductor folks, we're able to see these features and automatically target and test inside the nano indenter. Okay, so some examplos of strength testing. One of the things we're really pushing hard for semiconductors is stress strain curves by nano indentation. In fact, KLA has a patent for doing this. It's a very simple technique. We take advantage of the CSM technique to do this. And we can go in and measure local stress strain curves and estimate a yield strength and yield strain for metallic samples. And the advantage of this is we can do this on as manufactured parts. So we don't have to do this on test cases If you can cross-section and polish, for example, here, this is an A8C4 bump chip. If you can cross-section and polish, we can test it. And so we can do local stress strain curves. We can do hardness and elastic modulus maps of as produced parts. And this is huge because now you're testing the actual piece, which is the most important part. Strength is an interesting thing. In metals and ceramics, flexibility is fixed. There's no time dependent component to it. But in strength wise, metals and ceramics can exhibit time dependent deformation and time dependent strength. So this is process rate effects. You know, as these high volume manufacturers are trying to speed up the process, that means all the manufacturing parts, say for example the die bonding process, is moving at higher rates to accommodate that. And higher rates in metallic materials typically results in higher strengths. So this is something to think about during the process. This is an example of hardness as a function of indent displacement in indium. And each one of these curves is at a different indentation strain rate, right? And the higher strain rates up here, as you might imagine, result in higher hardnesses. This is something that a KLA nano indenter can probe very rapidly. Further, as we move into these very high rate processes, we can look at indentation strain rate versus hardness in this example here. And this is on commercial purity magnesium in this case. And we're looking at hardness as a function of strain rates. And we can get up into impact testing. And now we're measuring hardness and strength of a material on the order of microseconds. And looking to see how the material is affected by this and what strengths does that material operate at. Right? Okay. The last example then is something that's very critical to semiconductor devices, and that's stress migration. In the material science community, this is often called CREEP, or time-dependent plastic deformation. This example is in tin in this case, and this is on the left here. This is an indentation depth versus time curve. The time in this measurement is very fast. It's only 2 seconds, fully noting that tin creeps a lot at room temperature. But if you load up rapidly and hold the load constant, the depth continues to increase over time. And this is creep or stress migration. And we can take this set of data with our indenters and make a plot of indentation strain rate versus hardness. And we can take that data further and calculate a stress exponent. And then this data can be used in simulations during simulations for manufacturing processes and simulations for device performance and reliability. Okay, so flexibility and strength. The third one, and one of my favorites, is failure, right? And using the indenter to probe failure, to understand failure, and sometimes even force failure in order to get a better understanding. So when you look at semiconductor manufacturing processes, what are some sources of crack initiation and growth? Cracking is the most common source of failure in these materials. So you have contact stresses, impact forces, people dropping their phones, right? And then cracking screens, thermal expansion mismatch, fatigue, aging, irradiation, UV from the sun. Creep can be a source of failure and crack initiation. Processing inhomogeneities and flaws, and obviously chemistry and environment are an important role. Okay. Further, when you take all of these mechanisms and you look at the architecture of a chip, now these are even more complicated by all the different layers and components that are being stacked up with each other. Right? Okay, so one of the first things to think about when you think of cracking and failure is fracture toughness. And fracture toughness in general is, again, a very traditional technique used on bulk samples. As you move towards smaller and smaller scales, this becomes a tough thing to measure. So indenters can provide a measure of fracture toughness. There's some caveats to that, but it can provide an estimate. And as an example, this is BK7 glass. And we've taken a Vickers indenter geometry in this case, pushed it into the glass, and the result are these radial cracks that come off. And if you go and you look at the models behind fracture toughness, indentation fracture toughness, we can measure these crack lengths. We can take the load and come up with a value of fracture toughness. And in this case, we measured 0.96 MPa root meters. And if you go into to the manufacturer of this glass, on their table of properties, they come up with about 1.08 MPa root meters. So we're right there measuring a good value of fracture toughness on this material. So fracture toughness is important. When you can take then the indenter and think about fracture toughness in relationship to chemistry, environment, exposure, and processing, now you can study this even further and get an understanding of how your materials are going to evolve with time and change with time, chemistry, environment, etc. So one that we can put our indenters inside glove boxes or environmental chambers, and we can change things. We can change temperature, change humidity, change the chemistry, and probe the sample with the indenter and see what happens. So as an example of that, this is PMMA or plexiglass, and we put it into a environmental chamber with exposed to an acetone environment. And when you go in and you push on this material in room conditions, lab conditions, there's no fracture, there's no failure. But you put some acetone environment around it and do the same exact test, all of a sudden now there's a lot of cracking that's happening, right? So materials change with environment and chemistry, and nano indenters provide a very easy way to measure those changes, right? We can even do scanning surface topography to look at how the mechanical deformation is occurring and what's changing with environment, right? Okay, so one that I want to spend a little bit of time on here is delamination or film adhesion energy, because this is a very important topic for semiconductor manufacturers. They're depositing brittle films on top of insulators or brittle films on top of polymers. There's a lot of different combinations of materials there. And one of the biggest things is making sure that film sticks to the substrate, right? So the use case I want to highlight here is a piezoelectric material on insulator, POI. And the film in this case is an LTO film and lutetium titanate, sorry. And this is for 5G applications for cellular devices. And again, KLA is good at defect inspection, right? So we worked with our partners in Candela at KLA, and they identified a number of defects. And one of the main defects they observed was delamination lines on these POI wafers. And we said, all right, great, let us probe them with our nano indenter and see if we can learn something about the delamination or how that works. So we designed an experiment where we took a spherical indenter on this film and pushed in at different loads pretty rapidly, and just to see what happens. And what occurred was this cracking. So at a specific load, we started seeing delamination of the film, and the delamination got bigger and bigger with more and more load, as you might imagine. The other thing that happened was there was a significant failure event in the load displacement curve. And it turns out that prior to that loading and just after that loading, we start to see this delamination event, right? So we have very linear elastic loading to begin with, then there's some sort of failure event, and then now we have crack propagation at the interface. So we can take that information, we can go a little bit further, and this is a load depth curve here. And just before this what we call pop-in event, this failure event, again, it's a very linear elastic type response. Very, very little, if any, plastic deformation, and no cracking. Go a little bit, apply a load a little bit above this failure load, and all of a sudden now there's this burst of energy, and now there's a visible crack. So we can take that information, calculate an energy associated with that, calculate the size of the delamination using optical microscopy, and we'd come up with an adhesion energy based on this, right? And you might imagine we can go even further. We can start looking at energy release rates. We can look at a lot of different things with this type of test on this specific type of material on substrate. So again, the nano indenter solution here is working with our defect inspection folks, working with the manufacturer to say, hey, we think you have a problem. let us help you use the nano indenter to help you understand what you can tune in your process to make the strength better. So systematic detection of interface cracking. We calculate an adhesion bond energy correlated to yield and field failures. And then we provide them enough information to put a feedback loop in their model and their process to design better films on substrates. Again, so this is a forced failure event where we can actually learn something about that interface with a nano indenter. Okay, another way of kind of forcing failure and trying to learn something about it is scratch testing, especially for films. And so we have a very dedicated procedure that follows ASTM and ISO protocol of scratch testing and looking at delamination of films. And it's a very simple protocol. We scan the surface with the indenter first using these high resolution scanners. We look at the initial topography. In step 2, then we can apply, we come down, make contact, and apply a ramped load scratch. So we're continuously increasing the load as we laterally move across the surface. And during that event, things are happening. There's delamination, there's plastic deformation, there's all sorts of different failure events. And we use the displacement sensor to monitor those during the scratch test. Finally, we scan the residual deformation one last time with a very small load going across. Right? So the result of that is something like this. This is called profile, or this is the shape and topography of the surface as a function of scratch position. And here we're looking at the initial profile is very, very flat. As you might imagine, these are very nice thin films. During the scratch, we start to increase the profile, the topography here. There's a huge noticeable change right here, and this is correlated to spallation of material, right? It's cohesive failure of the film. As we continue to apply loading and movement, now we see extensive failure here. And now this is adhesive failure of the coating. The coating, it's popping off, and debris is flying everywhere during the scratch test at this point. So this might be a ultimate failure of this film, if you will. So we do that test, we scan after the fact and try to identify some specific things in the displacement data. And then we correlate the information to optical microscopy and try to get an understanding of what's happening. So this event right here in this example, this is this cohesive failure followed by an adhesive failure at the interface, right? And we can do this for different directions. We can do this for different places on a device and supply failure loads that can be then correlated to strengths and improve processes. Right? So scratch testing is another way to force failure to understand the material combination. Okay, last example, this is low-K thin films, again, scratch testing, and I just want to point out some more of the failures that we're observing. And again, it's this cohesive failure and adhesive failure during the test, and we can pick out very small changes in these loads to cause failure between samples that are meant to be pretty close to each other, right? So it's a really nice way of quickly examining failure of films on substrates. Okay, the last couple ones here are somewhat unique. As I mentioned, in high power silicon carbide electronics, defects play a critical role. And my understanding is it's all about getting rid of these defects in silicon carbide to produce better materials. And so nano indenters are neat because we can, and this is just kind of an example I want to throw out. Nano indenters are unique because we can force defects into the material. And that allows researchers to maybe study these defects, right? So this example here on the right, this is a silicon carbide thin substrate. And we've taken a cube corner indenter and pushed into this. And then the researcher in this case went to the TEM and looked at the dislocations that evolved around this indent. And so these are dislocations propagating on different planes within the crystal. And you can imagine then if you're trying to detect defects or trying to eliminate defects, this is a way of placing defects in there and trying to study the material and study what those defects look like so that you can improve your defect inspection processes, right? So kind of a unique way to use a nano indenter to force defects in there to learn more about it, right? Obviously you get cracking too that can be associated with this, and maybe those cracks also help in determining defect detection algorithms. In a very big change from kind of unique ways of looking at this, nano indenters aren't only for solid mechanics, for solid, stiff, hard materials. We can also, as I mentioned, look at polymer encapsulation, and we can look at some very compliant materials. And we do a lot in the bio community with this, but it also applies to the semiconductor industry in packaging. And so we can take our indenters and we can probe. In this case, this is an example of a PDMS, but we can also probe these gel coatings that go on top of semiconductor devices for environmental protection and packaging. We can look at load displacement curves. We can look at adhesion surface energies, and we can look at stiffness changes as a function of time, and then really characterize the viscoelastic properties of these environmental protection encapsulations. And that way ensuring that when you design the material to protect against certain vibrations or certain environments, that it's going to be it can mechanically withstand those vibrations. Right? Okay, so that a lot of examples, and to kind of summarize all of this stuff, nano indenters are typically thought of hardness and elastic modulus, or designed for these guys doing research at small scale mechanical test facilities. And over the years, we've really improved what we're able to do in semiconductor manufacturing. We've taken these ideas and applied them to very specific applications. So nano indenters are now playing a critical role in the manufacturing of semiconductor devices, all the way from new materials to quality control. Flexibility of the substrates, films, and components can be evaluated through the elastic modulus. This is a very critical piece of information for material models. Strength is characterized by direct stress strain data using flat punches, and also indentation hardness. And we can do this at different rates and different temperatures and different environments. Right? And finally, failure. Failure can be measured by controlled indentation. We can induce delamination, induce cracking, induce defects. And by that induction, we can then learn something about material behavior. So I hope this has been informative. I tried to avoid some of the science behind this, and I wanted to focus on specific examples that you may not have heard of a nano indenter being used in semiconductor manufacturing. Again, I want to thank Toyo for inviting me to this. It's my absolute pleasure to give these seminars, and I look forward to answering any questions. Thank you very much for your time.